Good morning. My name is Daniel Winklener, and today I will be telling you about our new commissioning results from the MIST-1 Multicusp ion source at MIT. The motivation for this work lies in particle physics, in neutrino physics to be specific. I will tell you a little bit about why we're interested in measuring neutrinos and how we are doing this with an H2+ ion source. After this motivation, I will tell you some of the design details of our ion source and then present the commissioning results along with simulations. In a standard model, we know of three active neutrino flavors: the electron, the muon, and the tau neutrino. They partner with the electron, the muon, and the tau, and they interact through the weak force. Now, in addition to this weak force interaction, there's another interesting behavior, and that behavior is neutrino oscillations. As the mass and flavor eigenstates of the neutrinos are not aligned, there's mixing. And this mixing means that neutrinos, as they travel through space and time, can actually change from one flavor to the other. Now, this was first confirmed in Super-K in 1998 and has since been observed in many other experiments. One of them is, for example, the Camlan experiment that's shown on the bottom of the page here. Here you can see the survival probability of electron antineutrinos as a function of the ratio of distance traveled to neutrino energy. And you can clearly see the oscillation wave. That is a smoking gun signal for these neutrino oscillations. Now, several of the experiments measuring neutrino oscillations have actually seen additional anomalies. One example is the LSND experiment that is shown on the bottom right here, where you can see a strong axis over the prediction in the low energy regime. And one possible explanation for these anomalies is the addition of a new so-called sterile neutrino that is not in the standard model yet. And this sterile neutrino would participate in the neutrino oscillations, but it would not interact through the weak force. And there are already several experiments out there that are aiming at measuring these sterile neutrinos or determining whether they exist, but none of them are actually discovery level. And so the ISODAR collaboration has designed an experiment that can definitively show that there are or aren't sterile neutrinos. And the way we do this is by bringing our particle accelerator that produces a 10 milliampere proton beam into the underground facility where there is already a large liquid scintillator detector for neutrino measurements. We couple our particle accelerator with a neutrino production target and produce a very pure electron antineutrino source. Now, these electron antineutrinos will then travel, some of them will then travel into the detector where they can be measured very precisely when they interact with the protons in the water or the liquid scintillator. And by doing with this, we can produce a plot like the one on the left here that is very similar to the Camlan plot that I showed earlier. On the horizontal axis, you have the distance traveled over the neutrino energy, and on the vertical axis, the survival probability of the electron antineutrinos in the detector. And so you can see we can trace out a very nice oscillation curve, and with this, we can determine whether or not there's 1, 2, maybe 3 sterile neutrinos, and also if there's an additional process involved, for example, neutrino decay. So we can get a lot of information from this. And as you can see on the sensitivity plot on the right, we cover nicely in this delta m squared sine squared 2 theta space the existing experiments taken together in a global fit process, as well as the reactor anomalies, which are also anomalies seen in reactor-based neutrino experiments. The question is, how do we do this? Because we need a factor of 10 more protons on target as similar compact particle accelerators can actually produce. And for this, we have designed a new cyclotron. It's a room temperature cyclotron. It's isochronous that operates in CW mode with an 80% duty factor. It operates at 32.8 megahertz in the fourth harmonic. It has 4 double gap cavities, which leads to a very high energy gain per turn. And there are 3 sort of novelties that we have combined in this machine, and one of them is to accelerate H2+ ions. The other one is to use direct axial injection through an RFQ, a radio frequency quadrupole, that is a very efficient buncher and also moderately pre-accelerates our beam. And then finally, we utilize vortex motion, which is a beam dynamics effect in the cyclotron during acceleration. I will, in this talk, focus on the production of the H2 plus ions, but please go ahead and ask me any questions that you might have about the RFQ and the vortex motion later in the Q&A session. We accelerate H2 plus instead of protons. This helps alleviate space charge issues. In a way, you can think of it as accelerating 2 units of charge for the price of 1 and stripping away the electron later to get the protons back. The drawback, of course, is that the H2 plus ion is heavier than a proton, and so the rigidity is higher. We need a larger magnet, and we have to accommodate this in the design, which we have. And we have found that overall there's a net benefit of using H2 plus in our machine. Now coming to the meat of the talk, the ion source, because this is the ion source conference. So the mechanical design of the MIST-1 ion source is based on the LBNL design by Ehlers and Lung. It's a filament-driven multicusp ion source. You can see here a CAD model where you can see in black the magnets. There are 12 radial magnets in a multicusp arrangement, and then we have 12 front plate magnets. Again, they're alternating in polarity, and on the back plate we have some additional magnets. And all of these are to confine the ions and the electrons inside the source for a longer time. Our electrons are produced on a hot filament, as shown here. Currently, we are using this spiral shape, which works pretty well, but we are investigating different types of filaments and different positions of these filaments also. The whole ion source is water-cooled. There are 3 water cooling circuits, one for the back plate, one for the source body, one for the front plate. And we have currently a preliminary extraction system installed and are working on the design of the extraction system to match the ion source to the RFQ. The electrical design is fairly simple. We are driving the filament through a filament heating power supply that is capable of delivering up to 100 amperes. Our filament typically runs between 30 and 45 amps. The discharge power supply is able to sustain a discharge at 150 volts maximum. We run it between 60 and 150. And the discharge current is typically between 5 and 15 amps. We have our source on a high voltage potential of up to 18 kilovolts, and then we have a tetrode extraction system with an Einzel lens element that can go up to 17 kilovolts. Power is brought up to the high voltage platform through 2 4 kVA isolation transformers, and we communicate with these power supplies through an optical USB extension cable. Now coming to the commissioning results, our highest current so far was 5.2 milliamperes total from a 4 millimeter extraction aperture, which corresponds to a current density of 42 milliamperes per square centimeter. And you can imagine that we are planning on opening up this aperture a little bit more to reach our nominal goal to drive the cyclotron, which is actually 10 milliamperes of H2 plus. The mass flow was 1.3 SCCM, discharge voltage and discharge current are here, and then the species ratio was tilted somewhat towards H3 plus, and that means this is not our desired operating point, unfortunately, even though it gives us the highest current, and that is because at very high mass flow, the recombination of H2 plus with a proton to an H3 plus is a preferred product. We reached our phase 1 design goal of larger than 80% H2 plus fraction out of the source by reducing the mass flow to 0.275 SCCM. We measured the mass spectra using our LEBT or diagnostic beamline with 2 quadrupole magnets and a dipole magnet. The second diagnostic box all the way on the left contains a Faraday cup with slits and 2 Allison emittance scanners. These emittance scanners will be important 2 slides from now. And the resulting mass spectrum of one of our most successful runs you can see on the right here with about 500 microamps of H2 plus out of our source. Here are some plots of our first systematic measurements. We varied the mass flow, which has the strongest effect on the species ratios. You can see this in the top right plot here, where you can see that the H2 plus goes down rather quickly with increased mass flow, and the H3 plus goes up. The protons are fairly constant, as are the contaminants, and again they are on the few percent level. The total current also goes up, and in this case we reached a maximum of 2.14 milliamperes in the first Faraday cup of this is the combined current of all the species in our ion source. So this is quite typical behavior, as again with more gas in the source you have more chance to recombine or to combine an H2 plus with a proton to an H3 plus, or H2 plus with an H2, etc. There are many collision processes that can happen in the ion source. We also varied the discharge voltage and the discharge current, and as you can see down here, these change the total current slightly, but they don't have a strong effect on the species ratio. Now coming to the promised simulations, we used IBCMU, developed at Uvascular, and then Warp for the beamline. This is for the ion source extraction simulations, and then Warp for the beamline simulations. And you can see again here the beamline setup with the diagnostic box first, then the quadrupole, the dipole, the quadrupole, and then the second diagnostic box. And you can see the beam envelopes on the bottom left here. And one thing you can see is that we lose lots of particles actually through this beamline, because as I mentioned before, this was built on a shoestring budget, and it's not an ideal beamline. So our transmission at best is about 50%. Sometimes it's down all the way to about 25%. What it lets us do, though, is measure the phase spaces using our Allison emittance scanners. These were built by undergraduate students, and they are working quite well. Here you can see the measured phase spaces on the top for one particular setting, and then the simulation on the bottom that match the numerical values quite well. And also you can see that qualitatively they agree in terms of what kind of effects you see from aberrations at the entrance and the exit of the dipole mostly. And knowing that these simulations match our measurements quite well, we can estimate the emittance after the ion source. Our measured emittance, this corresponds to the pictures I showed on the previous slide, are 0.37 and 0.28 pi millimeter millirad. These are RMS normalized emittances. And if we backtrace those through our simulations with Warp, we see that the source emittance is about 0.05 pi millimeter millirad. And this actually corresponds quite well to the IBCMU simulations of our ion beam extraction, and also to what we would expect from a multicusp ion source, because it has a fairly quiescent plasma, and if the power supplies are stable, then the beam does not come with a lot of energy spread or a large emittance. Before coming to the conclusions, I just wanted to take one slide to show you some lessons that we learned. And maybe there's one or two people out there who can benefit from our mistakes. And they're all about materials, really. Stainless steel, for one, is, while it's a strong material, and it's not a good heat conductor. We learned this the hard way, as you can see in the right picture here of our plasma aperture. We are now replacing many of the materials in our ion source with different ones. For most of them are copper alloys. One is elconite, which is tungsten copper, and others are Elmedur, for example. Second, O-rings. Not all O-rings are the same. Some of them outgas quite a bit, and then they contaminate your source, as you can see on the bottom left. We have replaced all of our O-rings with Viton, which changed things quite drastically. We now have below 4% contaminants normally in our ion source runs, sometimes even as low as 1%. And then finally, just try and reduce the number of flanges and connections and fittings in your gas line, in your ion source. I think this is just in general good advice. So in conclusion, MIST-1 has been commissioned at 25% power with good results. We tried many different things and we had a lot of fun doing this. Not all of the things were successful, but in the end we were able to reach our phase 1 design goals. And we're now upgrading the source, and hopefully at the next Ion Source conference we can present even more exciting results. With this, on behalf of the ISODAR collaboration, I would like to say thank you for your attention, and please let me know if you have any questions.